In this video I want to consider a technique for simplifying integration which uses something called partial fractions. And like the other techniques we've looked at, basically we're just trying to take an integrand which looks fairly complex and reduce it to something more simple that we can work with. So let me start off by doing something that doesn't immediately look related, but consider the fact that if we had two fractions, maybe something like this, 3 over x plus 2 plus 1 over x take 1, let's say, that we could add those together. We could express them as a single fraction by saying what 3 lots of x minus 1 plus 1 lot of x plus 2 over a common denominator of x plus 2 times x take 1, which is equal to, so what I've got in the numerator, 3x plus 1x is a total of 4x, and negative 3 plus 2 is going to be negative 1. And if we wanted to, we could expand out our denominator. So we'd have x squared, we'd have plus x, and we'd have minus 2. So the reason I'm doing that is just to sort of show the fact that we can take two what are fairly simple algebraic fractions and combine them by addition into an algebraic fraction which is a bit more complex. The reason for noting that is that if we were trying to integrate something of this form here, then we wouldn't at this stage have a technique which would work for us. We might think we could use substitution or use substitution because this is a quadratic and this is a linear, but we'd find that if we differentiated that it didn't actually allow us to use our change of variable technique. However, if we note that we could express this as the sum of these two fractions, well, those are both algebraic fractions that we can integrate. And these are called sometimes partial fractions as an alternative way of expressing this rational function here. So what we want to do with this technique is reduce a rational function like this into its partial fractions so that we can integrate something like that. Now, the textbook sort of gives a number of different kind of types of partial fractions that we could come up with. So there's its suggestion of three different scenarios we could have, that for every linear factor ax plus b in the denominator, so they're just linear factors like this, they're sort of ax plus b, there'll be a partial fraction of that form. So if our denominator contained two of those linear factors, then we'd have two partial fractions which would each just be a constant over one of those factors. So that's probably the main kind that we'll consider. If we get a repeated linear factor in the denominator, a sort of cx plus d type factor in the denominator, there'll be partial fractions of the form that plus that. And then it talks about, well, what if you get an irreducible quadratic factor in the denominator? So one of these that can't be factorized, an ax squared plus bx plus c that can't be factorized, then there'd be a partial fraction of that form. However, I think it's fairly safe to say that these ones aren't really the intention of the syllabus. The syllabus says use partial fractions where necessary for integration in simple cases. So I'm pretty sure it's thinking predominantly of these, maybe some of these kind. So let's consider an example of that form for our situation. So I'll take a question from the exercise. And some of the initial questions here are simply asking you to sort of do the partial fractions bit and not actually do the integration. But I think what we'll do is I'll just pick the first question here, and it's got a fraction like this, so 5x plus 1 over x minus 1 times x plus 2, and it's simply asking us to express that as partial fractions. But let's say we were actually going the extra step of trying to anti-differentiate or integrate that. So the first step would be to express the rational function using partial fractions. Now in this case, as in some cases, life's made a bit easy for us because the denominator is already factorized, but that could be expressed in expanded form, and just looking up here I notice it's exactly the same one I've got there. So it could be expressed as x squared plus x minus 2, and we might have to do the factorizing there. So let's let that rational function there be equal to partial fractions of the form a over x minus 1 plus b over x plus 2. So that's really just taking note of this one here, that for every linear factor in the denominator, there'll be a partial fraction of that form there. So when we do that, then we could say, well, therefore, 5x plus 1 over x take 1 times x plus 2 is going to be equal to, so on the right-hand side, when we combine these into a single fraction, give them a common denominator, there it is there. And so the significant thing here is that the numerators have to be equal, don't they? Because the denominators are equal, the only way the fractions can be equal is if the numerators are equal. So expanding and collecting our like terms, we've got an a times x here and a b times x there, so that's altogether an a plus b times x. We've got a plus 2a and we've got a minus b. So those numerators have to be equal to each other. Now, there's a couple of ways that that we can go about this, and in actual fact, I'm going to go back on what I've done there, because I think the well, of the two ways that I was thinking of doing them, I think the one that that leaves it in this form is probably easier. So let's, looking at the right hand side, if we were to let x equal negative 2 and then equate these, well, 5 times negative 2 on the left hand side is negative 10, negative 10 plus 1 is negative 9. And the reason for picking x equals negative 2 is that it makes this term here equal to 0, doesn't it? So I can pick x equals negative 2, and after I've equated them, then I'll do another one where x is equal to 1, and that'll eliminate this term. So basically, by letting x equals negative 2, eliminate that, I'll find out a value for b here. So negative 9 on the left-hand side. On the right-hand side, I've got b times negative 2 minus 1. So that's negative 3b, so therefore b is equal to 3. And now if I let x equal 1, then on the right-hand side I'll have 5 plus 1 is 6. And on the left-hand side, on the left-hand side I'll have 6. On the right-hand side, my second term with the b will be eliminated, and I'll just have a times 3. So therefore a is equal to 2. So from all of that, what I can do now is express this rational function, or more complex fraction, as the sum of a over x minus 1 plus b over x plus 2. So a is 2 and b is 3. So that's going to be 2 over x take 1 plus 3 over x plus 2. And both of those are anti-differentiable as logs, aren't they? So 2 times natural log of x take 1 plus 3 times the natural log of x plus 2 plus c. And there's my integral. So what we're aiming to do is to reduce a more complex fraction, algebraic fraction, into simpler what are called partial fractions. And then often, well, if the denominators are linear expressions in x, then we'll be integrating by using natural logarithms.